Dear students, we continue our discussing of topic 1, and today we are talking about vectors, which is an important part of chapter 1. The last part of it, you have come across scalars and vectors in the previous classes, and you have the idea of what a vector looks like. So naturally we'll build upon those concepts that you already have, and most of the time we'll be talking about the resultant of two vectors, but there will be situations which are more challenging as compared to what you used to have in O levels. We'll begin by the same idea that you studied in O level. What is the main difference between the two types of physical quantities that we categorize as scalars and vectors? Even in A level they ask questions like, what is the difference between scalars and vectors? So let's make that difference clear before we move further. Scalar quantities are those quantities which are completely described without any mention of direction. In simple words, they do not require or they do not need any mention of direction. So those quantities, scalars are those physical quantities that require no mention of direction for their complete description. That means mass is completely described without any direction associated with it. Time is completely described without any idea of direction attached to it. Similarly, density doesn't require any direction. So these are scalar quantities which do not require. But if I replace this word by vectors, vectors are those physical quantities that require a mention of direction for their complete description. That means force, which is a vector, remains incomplete, its description remains incomplete unless we attach some direction to it, unless we add some direction to the information, and that completes the picture. Displacement remains incomplete, it does not convey the full concept unless we mention the direction of that displacement. So vectors are those physical quantities which require direction if we want to completely describe them. Vectors are fewer in number when we compare with the scalar quantities, and those physical quantities which are always treated as vectors, I'm going to write them here and you must remember, because sometimes they ask question like in paper 1, which of the following is a vector, which of the following is a scalar. So you at least need to remember which quantities are always taken as vectors, because they are fewer, so it's easier to remember them. So we can start from displacement. Displacement is always a vector quantity. Velocity, force, and therefore weight, because weight is a force, so it is always a vector quantity. Then momentum, you will study it in chapter 4. Momentum will be a physical quantity which will be treated as vector. Then more in number, like time, mass, density, pressure, work or energy, power. All these are scalar quantities. These are scalars. And this list is quite long. There are many other quantities that we can add to this list. We can add volume to it. We can add speed to it. And we can add more and more quantities as we study the AS physics. There are numerous quantities that come in the discussion, and we keep talking about whether they are physical, whether they are vectors, whether they are scalars. So you learn about more quantities, and you can enrich these two lists. Now, after we know that certain quantities are treated as scalars and certain as vectors, we need to understand how we add vectors. So our next topic is vector addition. Addition of vectors. Two vectors are added in more than one ways. But the simplest of all is the situation in which vectors are either in the same direction or they are exactly in the opposite direction. Like one vector, which may be a force of, let's say, 3 Newton, could be added to a vector which is 4 Newton. These two vectors are added just like numbers. So 3 added to 4 gives us 7. So a 7 Newton force will be the resultant force when we add these two vectors. And this is the resultant force. This is the force that has the same effect as these two together. So that is why this is the resultant of these two forces. It has the same direction as these two have, and they are simply added like numbers. So magnitude is treated as the simple sum of the magnitudes of these two. So 3 plus 4 equals 7. But if I change the direction of one of these two, now they are still treated as numbers, but we add them algebraically now. By algebraically adding, I means we need to consider their signs. If this is positive, this is negative. So their signs are important now. So I will add 3 to minus 4. So I will have minus 1 in the answer. Minus sign signifies the direction here. So that means I will have 1 Newton force in this direction. So this is the resultant vector. This time it is just 1 Newton force, but its direction is to the negative x direction, because the negative appears when I treat these two numbers algebraically. taking care of their signs being this being positive and this being negative. So -1 Newton means 1 Newton force to the negative x direction in this particular situation. But what happens when the two vectors are exactly at right angles? That is the second situation. One vector, suppose this is a 3 Newton force, and the other vector is along this direction, and this is 4 Newton, and they are exactly perpendicular to each other. They are making 90-degree angle to each other. In this situation, we can treat them as the two sides of a rectangle. So therefore, I assume that this is a rectangle and these are two sides of this rectangle, and the diagonal is the resultant of these two. So we have a situation where a right angle triangle is created. 3 Newton, of course, can be considered here with its size same, and this is this direction. So these two vectors can be added using Pythagorean. So Pythagoras principle applied to it gives us the resultant here. If I denote it as r, r square is equal to 3 square plus 4 square. And if I want to know what r is, it is 3 square plus 4 square under root, which is 9 plus 16 under root, which means 25 under root, and which means 5 Newton. So this resultant is 5 Newton force, and its direction must be this. I have guessed its direction from the right hand, from the rule known as head to tail rule. And you are familiar with this. If this is one vector, which is 4 Newton, and this is another vector, which is 3 Newton, these two are obeying head to tail rule, and therefore this must be the resultant, which is 5 Newton. So using head to tail rule, I can correctly guess what is the direction of the resultant of these two forces. So these are two different ways in which we can add two vectors. Now we come to the third situation in which vectors may be added. The third situation is the one in which vectors are neither exactly in the same direction nor opposite. That is one situation that we discussed in the beginning. They are not at right angle to each other. This is the second situation we discussed. They are at any angle to each other, like if this is a vector x and this is another vector y. Now they are not exactly parallel and they are not exactly perpendicular. So when I draw them using using the head to tail rule, I redraw this vector so that the head of this vector joins with the tail of this vector. So let me redraw this vector here. This is vector y. So I have redrawn this vector y here. So the head of this vector x, if I make it here, it is joined to the tail of this vector y. The resultant from the principle that I term as head to tail rule, this is obtained by joining these two. But the question is, how do I know the magnitude of this vector? How do I know what is the size of this vector? It can have two answers. One is, if I have drawn these vectors to the scale, I know x exactly and I know y exactly, then the length of x will be exactly known, and that will be the magnitude of the resultant vector r. For example, if I know that x is displacement of an object and I have drawn it to scale, for example, if it is suppose 3 kilometer displacement and this is 4 kilometer, and I have chosen to make it 3 centimeter and 4 centimeter. Then if I accurately draw it, I mean this is 3 centimeter and this is 4 centimeter, then whatever centimeter I get here, the length of this vector r will be multiplied by the converted to kilometer, because I have chosen this scale. 1 kilometer is equal to 1 centimeter on my scale. So let's say I have this length is something like 6 centimeters. So 6 centimeter means this is 6 kilometer based on this scale. So this is one way of doing it. But this is not usually what we are required to do in A-level, because this is used to be the case in previous classes where you used to draw vectors and then from the length of the resultant you could find the magnitude of this vector. This time we follow a slightly different approach. We use cosine rule here. Cosine rule. And cosine rule tells us that if r has x has a certain magnitude, y has a certain magnitude, even if this figure is not drawn to the scale, but their values are given accurately, their values can be used here in this formula along with the angle given. Usually they give us some angle. Let's say they have given us this angle. This angle, let's say it is 30 degree. If this is 30 degree, I can calculate this angle easily, because this is 180 minus 30. So this angle appears to be 150 degree. So cosine rule can be written as r square, which means square of the resultant vector. This is equal to square of the magnitude of one vector plus square of the magnitude of the other vector y minus 2 times x into y cos of the angle opposite to the resultant, which is 150 degree in this case. So this is the cosine rule, and we use this rule to calculate the resultant. For in this case, if this is 3 kilometer and this is 4 kilometer, we put these values here. 3 square plus 4 square minus 2 into 3 into 4 cos of 150 degree taken under root of this all. This gives us the resultant, and this will be in kilometers. So our resultant can be calculated using this formula, and this is cosine rule. Let's discuss a few more situations like this, because we have a lot of questions of this type in the exam. there is a vector x here, and there is a vector y here, and there is an angle 60° between these two vectors. What is the resultant of these two? Using cosine rule, it will be very easy, because look at what cosine rule means. You complete this parallelogram, and this is the resultant of these two, because this is one vector and this is the other vector here, assumed here, and this is the angle that you need to consider now for cosine rule, because 60° is between these two vectors and this angle is opposite to the resultant. So like I consider this angle, which was opposite to the resultant of these two, I will consider this angle now. So how can we work out this angle? It's easy, because I know that this angle is same angle as this, because this line continues and this line is parallel to this, so this angle must be 60°. So once I know this is 60°, this angle is 180 minus 60, so 120, so 120°. So once again, it is r is equal to x square plus y square minus 2 xy cos of 120°. So this will be the resultant magnitude of this vector, which is from the head to tail rule is clearly the diagonal of this parallelogram. So cosine rule is helpful in all those situations in which the two vectors are not parallel, they are not exactly opposite, which we term as anti-parallel, and the two vectors are not exactly at 90° to each other. This is the situation, and this is the formula that will be helpful then. When vectors are at any angle to each other, we have to carefully draw the figure, or at least we can imagine it here. Even if I can imagine this figure here and do not draw it specifically, because we don't have time usually in the exam, all we have to do is we quickly imagine, like if I have this vector here, if I have this vector here, and I know their magnitudes and I know this angle, I do not redraw this figure. I quickly imagine what angle I have here, because I quickly realize that this is 60°, so this must be 120°, so this must be the resultant with this formula. So with some practice, you develop that understanding, you develop that readiness or quickness to decide whether this angle is what the value of this angle is. One problem that many students face is that when they are given this vector x and they are given this vector y, they tend to join the heads of these two vectors and they think that this is the resultant of these two. This is the sum of these two vectors. So they label it as x plus y. Remember, whenever you have the tails of the two vectors joined, or heads of the two vectors joined, like this is one vector x and this vector y is drawn here. Suppose this. So if this is x and this vector is y, or this is x and this vector is y, these are same situations. In one situation, their tails are joined here. These are the tails of two vectors because heads are free. It's like this. Two things diverging. One is moving in this direction, one is moving in this direction, moving from one common point. So this common point is where the tails of the two vectors can be seen joined. So in this situation, the line joining the heads is not the sum of two vectors, it is the difference of two vectors. It is actually x minus y. And similarly, the line joining the tails of two vectors, if they are joined at their heads, it is also the difference of two vectors. It is not the sum of two vectors. It is not x plus y. It can be either y minus x or x minus y. But we'll talk about this vector. This is the subtraction of two vectors. We'll talk about this in our next lesson. For today, you will practice all those questions in the past papers which deal with simple addition of vectors. I hope you can handle the simpler ones, but for more challenging one, we'll have a little more practice, and then we can have a worksheet based on them. And until then, you can keep practicing, but this one will be discussed tomorrow. Thank you.